I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, news of a dissolvable brain implant, public health fears for ultrasound, and why Spider-Man would really have to be extremely small.
Then we get sucked into the cosmic conundra that have stumped scientists for decades and continue to defy our understanding of physics. Black holes, what are they? And where do they come from? I'm Kat Arney.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now let's start with a look at the top science news offerings this week. And up first, how ultrasound might be harming your health. Ultrasound is any noise with a pitch that's higher than 20 kilohertz. That's 20,000 waves per second. These sounds are beyond the normal range of human hearing. And despite being silent, though, exposure to them has been linked to symptoms like nausea, headaches and fatigue in a small percentage of people. And now a review that's out this week is calling for measures to limit people's exposure to the sound. According to the report, the current safety guidelines are outdated, inappropriate, and they're based on poor statistics. After receiving several letters from people claiming ultrasound was affecting them, the review's author, Southampton University's Timothy Layton, decided to do some detective work, as he explained to Georgia Mills.
First of all, I went out with a little team of volunteers and we looked out to see what ultrasound was out there. And to be honest, we were quite astounded because there are devices that produce moderate levels of ultrasound, like some of these automatic door opening systems, which open when someone breaks the ultrasonic beam as they walk towards them. And some which produce quite intense ones. One, for example, was coming from the loudspeakers in the public address system in a rail station, which has a footfall of 3 million people. And there we found the reason for this is because under EU legislation, the operators of these loudspeakers have to at all times know that they're working in case they need to evacuate the building, saying fire alert, or whatever. To do that, they can't obviously say testing, 1, 2, 3 all the time. That would annoy people. So they send an ultrasonic signal between these loudspeakers in the belief that no one can hear it and no one will be perturbed. But these people were being perturbed. So I said to myself, okay, I've got to try and look at the guidelines that protect these people and see what there must be levels that control what we put out, and found problems in those guidelines.
What problems would you say these guidelines had?
There's a lot of guidelines, a dozen or more, and they all seemed to agree roughly. But when I looked into it, they weren't agreeing. They were copying each other. Each time a new country or an organization needed a new guideline, it just saw what was out there and copied it. And that gave the impression of consensus. And if you actually traced it back to the original evidence these guidelines were based on, you found a number of worrying things. They were based really on about 6 studies in the 1960s and 70s. And they were primarily looking at the scenario where a man would be operating an ultrasonic cleaning bath at work, and the guidelines would be based on a man in the occupational setting who could then put on earphones or be moved to another job or be protected in some way from the source because he knows he's being exposed. And I say man because these studies were primarily using tests on adult males. Now, we know that people lose their sensitivity to high frequencies as they get older. And in fact, many of these males worked in industry or had worked in the services and operated firearms. So they were really a bad set of people to test in order to produce guidelines to protect the public. You might have a grandmother who can't hear a high frequency holding in her arms a babe who can, not knowing why this child is perturbed. It's unreasonable to think that they would wear hearing protection to protect themselves. We don't know how many hours per day they would be exposed. And so the guidelines seem to be based on poor statistics and wholly inappropriate for protecting the public to the kind of exposures we see them being exposed to today.
But if ultrasound is, for the most part, beyond human hearing, how could it be causing these symptoms of nausea, fatigue and headaches? Well, Tim has a rather neat theory. When you're exposed to ultrasound, your eardrum vibrates, but the signal is not converted into a sound. However, other receptors do send your brain the message that your eardrum is indeed moving, and this discrepancy between signals could confuse your brain, much in the same way seasickness does.
And what symptoms do we get from seasickness? Headache, nausea, dizziness, fatigue, exactly the same set of symptoms. So I'm not saying that ultrasound is causing seasickness. I think way too early days to look at that, but I would like to put that on the table as something to knock down so that we can get off the ground some sort of attitude to people who come claiming to have ill effects from ultrasound that doesn't immediately dismiss them.
If you fancy trying your hat at some detective work, Tim has released an app for smartphones which can detect ultrasound. And it turns out it might be used in some unexpected places.
There are strange and bizarre claims by companies of things that they will do with ultrasound. There is a company in the States that says it's developing a system whereby instead of plugging your mobile phone into the wall to charge it, you just hold it up in the air and it'll beam ultrasound at it to charge it. There is even companies that claim to embed into adverts and websites a code, a beep, 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 at ultrasonic levels. So if you think you're in an anonymous environment like a hotel or an internet cafe, what they claim to be able to do for a fee is embed an ultrasonic code into the adverts, and your phone picks that up, the beep, 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 without you knowing. Your phone has software on it that you don't know about that identifies you and the thing you're watching, and then sends a signal back to inform the company of what you were doing. That's another area in which we as people are expanding into using ultrasound without the public knowing. And if we're exposing the public to such radiations, we need to get our public health framework accurate for that.
Georgia Mills speaking with Professor Timothy Layton about his review calling for further research into ultrasound, which he published this week in the Proceedings of the Royal Society A. Kat.
A dissolvable brain implant, which could revolutionise the monitoring of traumatic brain injuries, has been announced this week. In recent years, we've seen the increasing use of small implanted electronic devices designed to monitor signs and symptoms in patients or deliver drugs. But these implants often need to be removed surgically when they're no longer needed. Now, US scientist John Rogers from the University of Illinois has come up with a soluble alternative.
The particular device that we've reported in this current publication is designed to meet a current clinical need in the treatment of the patients who suffer from severe traumatic brain injury, and in particular to monitor their recovery process. So it goes into the intracranial space to measure pressure and temperature, because those two parameters are very important for a physician to track, because if they fall outside of a narrow window, it could have profound negative consequences for the patient.
So you've basically built this tiny wireless implant that goes in someone's brain. Does it completely vanish again when it's not needed?
Yeah, it completely goes away entirely. Kind of how do you do this? And it's a multi-material system, each one of which individually is soluble in biofluids to biocompatible end products. So magnesium, for example, is biocompatible. Magnesium hydroxide is a result of the dissolution of magnesium in biofluids. Magnesium is a part of a recommended daily diet. You find it in multivitamins. So you can kind of go through the list, and we've been able to identify a full complement of materials needed to do this. The clinical relevance in terms of function is during that critical recovery period when the patient is at highest risk for high pressure or high temperature. So the front end of that is about a week. So we've designed our devices to operate stably and reliably over that time frame, and then slowly degrade on a less critical time frame that's typically 2 to 3 months.
Although this is a device that does dissolve, so you don't have to take it out again, presumably you have to get it in. How would it get into patients in the first place?
Well, that's a good question. I mean, the utility of these kinds of intracranial monitors, even the non-resorbable ones that are used today, are typically most important in pretty severe, traumatic brain injury cases. We're not talking about people who come into the hospital and have bumped their head. These are, traumatic events. And in most cases, the sensors can be inserted at the tail end of a surgical procedure that needs to happen anyway. So the intracranial space is open for that purpose, and the devices just slip in at the final step in that intervention, right? If the skull is not opened in that context, then what people do today is they create very small burr holes through the skull and insert the devices. And so their miniaturization becomes an important aspect of the device design, because you want to minimize, the impact on the patient getting it in. So in that sense, the physics of the way that our devices work are compatible with downscaling, even to a further degree than we've demonstrated in this paper. Devices about the size of a grain of rice, but they could be much smaller.
Could this kind of technology be used for anything else, not just monitoring signs and symptoms in patients?
Yeah, I think there are a lot of other functions that could be interesting. For example, going beyond just sensing and monitoring to stimulation and intervention. So we have parallel work, as an example, on resorbable devices that do electrical stimulation of the peripheral nervous system. And if you look at the healing of peripheral nerves, there's data in the literature that indicates that if you stimulate electrically that damaged site in an appropriate way, you can actually significantly accelerate the healing process. And then once the nerve is healed, you don't need the device anymore, so you'd engineer it to just dissolve away.
That was John Rogers from the University of Illinois, and he announced that work in the journal Nature.
You're listening to The Naked Scientist with Chris Smith and with Kat Arney. If you'd like to get in touch, you can email chris@thenakedscientist.com. You can find us on Facebook, or you can tweet @NakedScientists.
Still to come, what the grave findings from under a building site near Cambridge are revealing about our ancestry.
Plus, we'll be delving into black holes, including the supermassive one at the centre of the galaxy. Now, have you ever dreamt of climbing up the outside of a building a bit like Spider-Man? Making that dream a reality would require specially adapted adhesive feet that can take advantage of weak molecular forces of attraction between your body surface and the wall in the same way that a gecko does it. Felicity Bedford spoke to David Labonte from Cambridge University, who's been investigating whether there's a good reason why this wouldn't work for humans.
There's only a certain range in sizes that actually use a sticky pad. So you find tiny mites, you find big geckos, you find frogs and spiders and many different insects in between. And the question that we were interested in is whether there's actually a limit, or what is the limit to the size that you can grow to where you can still use adhesive pads. And there's an interesting problem hidden in trying to stick to surfaces, because as you grow in size, the amount of surface area that you have per body volume goes down. And it's probably easiest to illustrate that problem if you think of a tiny ant. If you look at the ant, you mostly see surface area, and there's a tiny bit of volume. And if you look at an elephant, you see a lot of volume, but there's really not much surface area.
It's difficult to imagine an elephant climbing with sticky feet. You mentioned quite a diversity of different animals there, from insects all the way through to reptiles. Are the sticky pads and the mechanisms that they use to climb the same across those groups?
From all the evidence we have, they're surprisingly similar. And in fact, adhesive pads in climbing animals have been a prime example of what evolutionary biologists call convergence, where you find the same solution appearing in very different animal groups. So if you think, for example, of spiders and geckos, so they're really, really different animals in terms of their evolutionary history. But if you look at their feet, the structures look almost identical. And this, of course, hints at the possibility that these structures are really good in what they do, and therefore they have evolved multiple times independently.
So what do these structures look like?
So on feet of geckos and spiders, beetles and flies, you would find what we call hairy pads, and essentially a dense arrays of tiny little hairs. And on the feet of many ants and cockroaches and tree frogs, you would find what we call smooth pads that are essentially unstructured, at least on a macroscopic level, so you can best think of them as a soft cushion.
In front of me, we have a range of different machines.
Yeah, so what you're seeing here is one of the devices that we can actually use to get an idea of how well animals can actually stick. And what you see is a centrifuge here. So essentially we can spin it around at different speeds, and we can put tiny little insects on the centrifuge so that they're spun around, and at some point they start to slide outwards. And using very simple physics, we can calculate how much force is actually acting on these animals and is pulling them outward.
So it's a bit like a merry-go-round in a play park, except insects, not children.
Exactly, and that for insects it's really not very dangerous because they're small enough to not be harmed at all by these techniques.
Can we switch it on?
Yeah, of course we can. If we look at the ant right here now, and then we now switch it on, and it slowly increases in speed, then you can see at some point the ant slowly starts sliding outward. So that's a point at which it starts to slide. And then if we go faster and faster and faster, suddenly it's off the surface.
That's quite impressive, really. It's certainly not something that I would be able to do if this was scaled up.
No, some of these ants can actually withstand forces up to 1,000 times their own body weight. So it's really, really impressive what they can do with their adhesive pads.
We're all familiar with the Hollywood version of sticky pads in the form of Spider-Man. How accurate is their representation of him clinging by his fingertips?
So, of course, there's a large number of issues if you talk about the scientific accuracy of Spider-Man. But if you phrase the question differently and say, well, why are there no larger animals with adhesive pads, then we can start saying something about this. Because if we scale up our calculations or our data that we have, then we find that if you go to the size of a human, you probably end up with an unrealistically large fraction of your surface area that needs to be covered in sticky pads. And what we calculated is roughly something like 40% of your total body area or 80% of your frontal area, which I think is UK shoe size 89.
That's going to make it difficult to climb.
Exactly. Exactly. And that's just to illustrate the problem that you face if you grow bigger and bigger. That comes from very simple physical laws that effectively pose constraints on what evolution can actually do.
Larger animals, many of them do climb.
So if you go larger than a gecko, say, for example, or if you go to a certain size, then what starts to happen is that suddenly the world doesn't look flat to you anymore. If you think again of an ant and it climbs on a twig, the twig is effectively flat for the ant. While if you think of a monkey, the monkey can actually grasp around the twig. And that's why you start to see a departure from these clinging pads or adhesive pads going to something like hands or massive claws and so on and so forth.
Spider-Man does whatever a spider can, but now it turns out only if he weighed about 20 grams. That was Felicity Bedford with Cambridge University's David Labonte. Now to scientific misconceptions. What flawed science dogma are you debunking for us this week, Kat?
This week, I'm sticking the needle into a topic that's particularly contagious at this time of year because it's the season for coughs and colds. While we might say we've caught the flu when we really just have a heavy cold, or joke about the men in our life suffering from man flu, the real thing, caused by the influenza virus, is deeply unpleasant and can be fatal for vulnerable people such as the elderly and those with certain health conditions. Earlier this week, I rolled up my sleeve for my annual flu jab, admittedly a couple of months late. As someone who suffers from asthma and who also remembers the horror and subsequent months of hacking coughing due to having caught swine flu back in 2010, it's as an important part of my winter routine as buying more pairs of thick black tights and remembering where I put the hot water bottle. But just as with other vaccinations, there are several unfounded myths about the flu jab floating around, which might stop people who need it from taking up the vaccine. And one of the most common is the misguided idea that the flu jab gives you flu. To explain why this is wrong, we need to take a step back and look at what's actually in a flu vaccine and how it works. Like many other vaccines, the adult flu jab is made up of inactivated flu viruses designed to safely train the immune system to recognise the infection and fight it off, should you encounter the real thing in your daily life. But while the immune system can recognise them and get ready to mount a response, there's no way these dead viruses can actually cause the illness itself. And even though the child flu vaccine, given as a nose spray, does contain live flu viruses, these are very, very weak and can't cause the disease. So where did the myth that having the flu vaccine gives you flu come about? Again, like many other vaccines, having a flu jab can leave people feeling a bit rubbish, including having aching muscles, feeling tired and even getting a slight temperature. This is due to the immune system swinging into action to prepare itself rather than flu. And there's also a chance that someone who's just had a flu jab may catch flu by coincidence, or just get a nasty non-flu cold that the jab wouldn't protect them from anyway. It takes up to 2 weeks for full protection to kick in after a flu jab, but just a few days for a real flu infection to take hold. So if someone's infected just before or just after their flu shot, they're still going to get the flu. And the jab doesn't offer protection against all the strains of influenza virus that might be out and about in the wild in any given year. So while the flu vaccine isn't perfect and it can't protect you against colds caused by non-flu viruses, it's still a lifesaver for vulnerable people. And although my flu jab didn't give me flu, I did feel a bit off colour afterwards, so I went back to bed for the afternoon. That's my excuse anyway, and I'm sticking to it.
Thank you, Kat. I wonder why you were late for the programme. Meanwhile, if you at home have something you'd like our scientific Sherlock to probe for you, do drop us a line with your suggestions to chris@thenakedscientist.com.
Recent building works in Oakington near Cambridge have uncovered an Anglo-Saxon burial site. With the help of DNA experts in Australia, archaeologists have used the human remains recovered from the site to build an Anglo-Saxon genetic profile that they've been able to compare with modern Britons. This is revealing how these European immigrants 1,000 years ago mixed with the general population. Greer Jackson went to meet archaeologist Richard Mortimer at the Museum of Archaeology and Anthropology to see what the research has been turning up.
The Anglo-Saxons are the formation of England as we now know it. Because by the end of the early Anglo-Saxon period, by about 700 AD, England has become physically what it looks like today, in the fact that all of our villages and most of our towns is formed or is forming by about 700.
So there's a collection of about 20 objects here. They all look like gold, but I'm sure they're probably not. People would have been buried with these things. Talk me through, what are these?
Well, they are gold. They're gold gilt. They're bronze underneath and then gilt gold on top. And they are, frankly, amongst the most beautiful things you'll ever find as an archaeologist. These on the right, these large ones, they'd be for ladies to wear, and they would hold with a pin, hold your dress up there together.
They're brooches then. They actually are massive. Some of them are bigger than my hand. They almost look like door knockers, to be honest.
Yes, they do. I can't deny it.
And I can see necklaces and combs. I assume they look like little keys on key rings, but I assume they're not that.
These things, yes, they are. They're girdle hangers. They are formalised key sets. In fact, one of the women, fantastic woman, one of the women at Oakington, buried, oddly enough, with a cow. That's not only unusual, in fact, it's a first in Britain, it's a first in Anglo-Saxon Europe. Nobody's ever been buried with a cow before. And she, the cow lady, got the keys to every lock and every latch and every box in that settlement.
Why on earth would you be buried with a cow?
Absolutely no idea whatsoever. It's because it's a first, you have to just try and make up your own reasons, I could just do it anyway. We're telling stories half the time, not telling truths.
Women buried with cows and made-up stories aside, this site is extremely important in our quest to understand our British heritage. Over 100 people were buried at Oakington, and they were in good enough condition for scientists like Dr. Richard Durbin to extract DNA and find out just how Anglo-Saxon we really are.
So we do is we take a bone, in fact in our case we took the teeth, which are kind of protected by the enamel. We sent those to an expert laboratory in South Australia, where they purified, removed all the DNA from the outside so as to get rid of any contaminating material, and then ground it up and isolated a very small amount of DNA. And very sensitively, we then brought that back, and because it's been degraded, it's in small pieces. So technically, this is a hard thing to do. It's become feasible over the last 5 years or so, and there have been a number of studies, but this is the first study of British samples from more than 1,000 years ago.
And what, you compared that data with modern humans?
Yes, what we did is we looked at some of those places where there were clear differences, which were rare and recent, which could tell us a lot about where people came from. And then we looked in the ancient samples to see who they shared most with and where they fell in that spectrum of modern variation.
And so how Anglo-Saxon are we?
Well, it turns out that modern English are about, in the east of England, are about 38%. But if we go further west to Cornwall or to Wales, that fraction drops. So we're all a mixture of the people who were here before and the people who came in the Dark Ages.
But why is it that, say, modern Welsh are only 30% Anglo-Saxon versus east of England being 38% Anglo-Saxon?
I would presume that is because people coming into the country, predominantly settled in the east and only progressively moved further afield into the west of England.
So it sort of matches the migration pattern. The Anglo-Saxons came over from Europe and landed in the east of England and then migrated west and north. And that's why you see less of this genetic influence on the Scottish and the Welsh and people from Cornwall. Yeah. It's said quite often you share, 50% of your genes with a banana. And within species, the human race, it's something like 99.9% or whatever it is. So surely, given that Europeans and these sort of local inhabitants from the Iron Age would have shared a lot of their DNA, what sort of mutations were you looking for to distinguish these populations?
So yes, we're all Northwest Europeans. We're genetically all quite similar to each other. So the differences are subtle. Although we only differ from each other at 1 in 1,000 places across 3 billion bases, that amounts to several million differences. Sometimes new mutations happen. That's what gives rise to differences. And ones that happen within a country, within, say, Denmark, will tend to be found only in the Danes or in people who mate with them. So we were looking for those very rare mutations to use them as tracers, essentially, of identity.
And so you say us in the East are 38% Anglo-Saxon. Often you hear that you're about 2% Neanderthal as well. So what's the remaining 60% of us?
Modern humans originated in Africa and left Africa about 50,000 years ago. And at that point, they met other human species, the Neanderthals, who had left several 100,000 years ago. And there was a bit of intermixing at that point, which contributed about 2%, we think. And then within Europe, initially there were hunter-gatherer peoples who did the cave paintings that one finds in France and Spain. And then after the Ice Age, the farmers came in and moved across Europe from Turkey, we believe now. And then there was a later movement of peoples bringing iron-working or metal-working technologies from Russia. So all of these things have left genetic traces that other people have been studying. We know that the people from Britain are a mixture of all of those.
An area of further research.
So it's an area of further research. I think this is just beginning now, and that, I think, is alongside the medical advances that we obtain from understanding how the genome works in the body. It will tell us a lot about our history as in people and about evolution. It's a very exciting time to be a genome scientist.
Certainly is. The Wellcome Trust Sanger Institute's Dr. Richard Durbin, and before him, Richard Mortimer, Senior Project Manager at Oxford Archaeology East. You are listening to The Naked Scientist with me, Kat Arney, and with Chris Smith.
And now we're going to move on to our main theme for this week, which is black holes. These are mysterious regions of space containing objects with sufficient gravity to bend the fabric of space itself, called space-time, in such a way that nothing, not even light, can get out. And this is why they look black, because no light comes out of them.
The idea of black holes was first put forward in the 1700s by an English amateur astronomer called John Mitchell. He used Isaac Newton's equations to reason that such an entity could exist. The mathematician Simon Pierre Laplace also came to a similar conclusion around about the same time, but neither of them had any evidence that black holes were real.
Well, since then, thanks to modern science, dozens of black holes have been detected just in our own Milky Way galaxy, including a huge one at the galactic centre, and millions more are thought to exist out there.
I think one where all my money goes into. But what are these entities? How did they form? And how do they work? That's what we'll be probing this week. And to start the ball rolling, Georgia Mills met with Cambridge University Institute of Astronomy researcher Matt Middleton.
A black hole, in its simplest possible terms, is an object that is incredibly dense, and the speed that it takes to get away from an object is related to how dense it is. The more dense it is, the faster you've got to go. And there's a point at which it's so dense that not even light can escape from its surface.
Like being the fastest thing in the universe.
Yes, absolutely. In terms of a more rigorous understanding, you can imagine there's, for instance, those games we used to play in, I think, the McDonald's, where you used to throw a coin around and it has that funnel shape. You imagine being the coin and trying to get out of that machine. And not only are you doing charity a massive disservice, but it's also very, very difficult. And you can imagine trying to go at the speed of light and still not being able to climb out of that thing. That's kind of what a black hole is. You know, it's this pit that when you go beyond a certain point, you can no longer escape.
This point of no return is known as the event horizon. We can't see inside because any light that made it there won't escape. But somewhere inside this is what's known as the singularity. This is where all of the mass of the black hole is contained in a minuscule area. And to fit all of this mass in such a tiny space, the singularity has to be practically infinitely dense, which pushes our understanding of physics to its limits. So how are black holes created?
Stars are in constant battle against themselves. They're producing all this radiation. That radiation provides an outward push against the inward pull of gravity. Eventually, stars sadly run out of fuel, and then gravity's going to win. It collapses in on itself. As it collapses in, material gets thrown away in what we call a supernova explosion. And these are really, really big, powerful events.
Most stars collapse down to smaller, stable sizes. But if they were big enough, the gravitational forces involved are so strong that nothing can stabilise them, and they collapse down and become a black hole. These black holes can grow bigger over time, sucking in anything that strays close enough, from planets to stars, and even, potentially, other black holes. What about when you get close to the event horizon? This is when things start to get a little weird. I'll give you an example. Here's an alarm clock. Let's push it towards the black hole. The ticking gets slower and slower and slower. So what's going on?
I don't know what it takes for you to hate a clock enough to throw it into a black hole.
I don't like getting up
You
in the
really
morning.
don't. We've all been there, haven't we? Okay, so the clock, if it's ticking, it's going to get slower and slower and slower because it's approaching the black hole. It's on increasingly curved space-time. And there's this thing called gravitational time dilation. And what we know, and what in fact we observe, is that clocks run slower the closer they are to a massive body. We've observed this around the Earth. So for the clock, nothing's happening. It's just ticking at a normal, happy rate. But for us, it seems to be ticking slower and slower and slow until eventually it will appear to be stopped ticking at all. That's when it's essentially at the event horizon.
Well, now my clock's been destroyed. I've decided I want it back. I'm going to throw myself into the black hole. From my point of view, what would happen to me?
Right. Okay, some seriously bad things are going to happen to you. So there are these things called tidal forces. We know tidal forces, they affect the Moon-Earth system, tides, yada, yada, yada. It's why if you were falling towards a body, your feet would feel a greater pull initially than your head, so you'd be stretched out. If you take that to the next level, in a black hole, you get thinner, 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 and you become spaghettified, which is it's a nasty sort of nasty word. You start to see some crazy things, like if you looked to your right or left, you might be able to see the back of your head due to photons traveling around a black hole caught in an orbit. So it would probably be quite a crazy trip. And eventually, of course, sadly, you'd be pulled inexorably towards a singularity where your mass would be collapsed down to infinity and you'd contribute to the mass of the black hole.
Okay, I've been putting you through your paces with all these questions. I'm going to send you some quick fire questions now because we get a lot sent in from the audience. But everyone's very curious about them. Yeah. So, first one, can black holes move around?
Oh, absolutely. Absolutely. I mean, in orbits, they don't sort of just jiggle around or anything. All you really think of it as is an object, right, with a mass. So absolutely, that mass can interact with other masses and be perturbed and move around all over the place, sure.
How common are they compared to other stellar objects?
Oh, rare. I think the upper limit for stellar mass black holes in our galaxy is sort of like 100 million, something like that. But we have billions upon billions upon billions of stars. There's millions and millions and millions of them possibly, but you're not going to look out and go, "Oh, black hole." Okay,
with your binoculars.
Yeah. You know, say, "Oh, what's that coming towards us? I can't see it. It's black."
Not another one.
Not another one. Yeah.
Do black holes ever die?
In principle, yes. So there's this thing, Hawking radiation. If you imagine that a particle is created on the event horizon and it breaks in half of it can go in, half of it can come out. So if you have these things called imaginary particles, you have like electron-positron pairs. Some comes out, some goes in. But that thing that's gone out is carrying away some energy and therefore mass of the black hole itself. And this is what's called Hawking radiation. Now, eventually, if a black hole sat on its own for long enough, eventually there'll be enough loss from this for it to die. But the rate at which it loses, the rate at which it evaporates, is proportional to the mass of the black hole cubed. So the bigger your black hole, the longer it's going to take. And so, eventually they will die, but they're going to take sort of the lifetime of the universe to do so.
Final question then. Will the Large Hadron Collider create black holes?
No.
Okay.
Do you want slightly more information?
Slightly more
information. Okay. The energy required to make a mini black hole, which is what they're worried about, is 10 to the 19 GeV. The Hadron Collider runs at a few TeV, so it can't do it. You're out by huge orders of magnitude, right? What was postulated was that if we have multi-dimensional space-time, that you could lower the threshold for making a mini black hole to a few TeV, and then there was the possibility that the Large Hadron Collider, when it hits these protons together, could create these mini black holes. But Hawking radiation would remove these black holes almost instantly. So these things would just gone. So we're not to be worried.
Oh, that's a relief. Matt Middleton was speaking with Naked Scientist Georgia Mills.
Now we've got the basics out of the way, time to go a little bit deeper. Now, supermassive black holes, which sit at the centres of galaxies, can have masses 10 billion times bigger than our sun. And despite being black holes capable of locking in light, they've actually been linked to some of the brightest lights in the universe, and these are known as quasars. Manda Banerjee, who's from the Institute of Astronomy at Cambridge University, investigates them. Hello, Manda.
Hello.
So what actually is a quasar then? What produces this light?
Quasars, as you said, these are the brightest lights that we see in the universe. And basically what they are very powerful, very energetic emissions that are coming from the immediate vicinity of these supermassive black holes.
Are they visible light that I could see with my own eyes, or would I need a fancy telescope to see this sort of light?
Quasars do emit in invisible light, but they also emit in all parts of the electromagnetic spectrum, so all the way from X-rays to radio waves.
And is that the clue that this is not just a star we're dealing with here? Because the fact that you're seeing all these different ranges of colours of light, all these different wavelengths, and stars don't do that.
Yes, absolutely. So that is one of the biggest clues, all of this emission in all parts of the electromagnetic spectrum, that we're dealing with something very powerful, very energetic.
And what do you think is going on then to do this?
So what you need to do to power a quasar is basically to dump a whole load of material, a whole load of matter onto these supermassive black holes at the centres of galaxies. So when you have lots of material, lots of gas, dust, stars being funneled into these central regions, all of that material gets heated up and it shines very brightly as a quasar.
So this is sort of a black hole with indigestion. It's lots of material trying to pile in very fast.
Yeah, it's a feeding monster of a black hole. So quasars are really the feeding phase of a black hole, where we're seeing them as they're devouring all of the material up around them.
Do they have any effect on the galaxy in which they sit by virtue of just existing?
Yes, so this is one of the main reasons that we study quasars, is because we now know that they have a very profound impact on their host galaxies. So we know there's a supermassive black hole living at the centres of most galaxies in our universe. And when these supermassive black holes feed during this quasar phase, all of this energy that they're outputting into their host galaxy, that can have a very dramatic impact that can blow gas, dust, stars out of the whole galaxy. And so in that way, it actually can control how big a galaxy will eventually get.
So it does have an important modelling effect on the ultimate structure of the galaxy. Can you also look at it the other way, which is to say, if I look at the structure of the quasar and its behaviour, can I deduce something about the black hole that is giving rise to it by studying it? And that tells me something about what the black hole is doing itself.
Absolutely. So we look at this quasar emission, and by looking at the gas and dust that's being eaten up by this black hole, we can infer lots of interesting things about the black hole, like how big it is, how massive it's going to get.
Manda, thank you very much. Manda Banerjee, she studies the brightest lights in the universe, the quasars, at the Institute of Astronomy in Cambridge. You're listening to The Naked Scientists with me, Chris Smith, and with Kat Arney. Now, we're delving into the physics of black holes this week, and still to come, Stephen Hawking thinks black holes are hairy. We'll find out why.
So far, we've talked about what's going on outside a black hole, but what about trying to glimpse what's happening on the inside? The event horizon at the mouth of a black hole is the point of no return. Once something crosses this threshold, there is no going back. The same is true for light, so it's proved difficult for astronomers to physically see what's going on beyond this point. But there might be a way to do it by looking at the shadow cast by the event horizon. Speaking with Georgia Mills, Shep Dolman is an astronomer at the MIT Haystack Observatory and Harvard-Smithsonian Center for Astrophysics, and he's part of an initiative called the Event Horizon Telescope Project.
There's a part of the universe that is forever separate from our experience, and that's inside the event horizon. And the size and the shape of that event horizon is predicted by Einstein's equations, which have withstood all the tests that we've subjected them to in the solar system, in the larger universe. And now we'd like to go to the one place where they might break down at the event horizon itself.
Past the event horizon, by its very nature, you can't really see into it. How would you be able to study something like that?
Well, in a paradox of their own immense gravity, black holes, which by definition are dark, are some of the brightest objects in the universe. And you can think of it this way. The black hole is insanely powerful, and it's trying to attract all of this gas, dust, and ionized plasma into a very small volume. And you get a cosmic traffic jam. Everything is rubbing up against each other, and just as your hands get warm when you rub them together, all this gas and dust heats up to billions of degrees. So it's a little bit like trying to suck an elephant through a straw. It's very hard to do, and when you ultimately do it, it's a big mess. So the black hole and the event horizon are illuminated by this three-dimensional flashlight that lights up the space-time. And one of the characteristics of the event horizon is that the light gets bent by the gravity, and so you wind up with a shadow feature. The way you can think about the shadow is that the light that is moving away from you, from the backside of the black hole, gets bent around in these curved trajectories back towards you, so it illuminates a ring of light around the event horizon. And it's the size and shape of that ring that we're after with the Event Horizon Telescope project.
So how are you planning to find this shadow?
Black holes are the smallest objects that we know of. And to see something that small, you've got to make an entirely new kind of telescope. So we need something, to put it in perspective, that has a magnifying power that's at least 2,000 times better than the Hubble Space Telescope. The best candidate for us to observe one of these black hole shadows is in the center of our own Milky Way galaxy. And radio waves are the perfect medium for that. They can pierce the gas and the dust and the ionized plasma that lies between us and the center of our galaxy. So we need to make a telescope that has 2,000 times the magnifying power of the Hubble that sees radio waves.
So the problem here is that you need a radio telescope that's 2,000 times stronger, and that would, to me, seem like it would need to be bigger. How are you going to go about this?
The magic of the Event Horizon Telescope is that we don't make one single telescope, but we use radio dishes that are spread around the globe. And we link them together using GPS to synchronize them perfectly. And then we install atomic clocks at each of the sites. And all of the telescopes swivel to look at the black hole at the center of our galaxy at the same exact moment. And when that happens, you get an Earth-sized virtual telescope. And the radio waves are recorded perfectly at each of the sites. Then hard disks are shipped back on a 747 or the airliner of your choice to a central facility. And when you do that, you wind up getting a data set that's equivalent to having a telescope the size of the Earth. And I would hasten to add that when you're making an Earth-sized telescope, you need an Earth-sized group. I'm just pleased as Punch to work with some of the most talented astronomers on the face of the Earth, from Taiwan, Japan, Chile, the United States, Europe. It's a really big enterprise.
This kind of massive collaboration thing, that it seems to me what science is all about. How did you get all these different telescopes on board with you?
Part of the secret sauce of the Event Horizon Telescope is that we're not building any new telescopes. We're developing all the instrumentation that allows us to turn telescopes that already exist into this global linked array. So what we have done is we've gone to the directors and boards of telescopes around the world. We've explained this project to them, and the science payoff is so interesting and exciting to the community that they've allowed us to come in with specialized equipment, install it at the telescopes, and make these observations. And we've had some very interesting results so far. We wouldn't really be having this conversation if we hadn't already seen very small shadow size features towards the black hole at the center of the galaxy. And now we want to take those size measurements one step further and see if we can make an actual image.
And then at some point in the near future, well, when is this going to happen? When are we going to get the telescopes to join up and assemble and all point at the same direction at once?
Well, we're on, as they say, an aggressive timeline. We have already made these precursor observations which show us that we're on the right track. And we are, over the next year, finishing the build-out across the entire global array. The first possibility for us really to make an image would be in the spring of 2017. That's when one of the largest telescopes, the ALMA array in Chile, will join the Event Horizon Telescope. And that will increase our sensitivity by a factor of 10, and also increase our resolution by about a factor of 2. And that will be the first time when we would have a shot at making a credible image. Knowing that all of those 4 million suns are within that ring would be the strongest evidence that we have, at least as humans, other aliens might have better evidence, that black holes actually exist.
What an exciting project. That was Shep Dolman from the Event Horizon Telescope, and he was speaking with Naked scientist Georgia Mills.
So we've looked at the bright lights we can see from black holes and how you might even be able to photograph one. But in general, black holes are so far removed from what we can see and test that they're the playground of mathematicians and theoretical physicists. This month, Stephen Hawking, the king of black hole physics, published a paper stating that black holes have hairs. To help us unpick this idea, we're joined by Dr. Andrew Pontzen from University College London. Hi, Andrew.
Hello.
So, what is this about? I mean, hairs like the hair on your head? Are black holes hairy? What's going on?
I do occasionally wish that some of my physicist colleagues would be better at naming things. This is possibly the least useful name anyone's ever come up with. But the point is supposed to be that if you look at Einstein's theory of general relativity, which is what underlies everything that we've been talking about today about black holes, it makes a very firm prediction that everything about a single black hole, you're looking at a single black hole, it is completely summarized by just three numbers. And those three numbers are its mass, so how much stuff is in there, its charge, so, if you throw something in that's got static electricity on it, it can keep that, and also its spin, how much it's spinning. And according to general relativity, that's all there is to know about a black hole. Absolutely nothing else to know about it. And when we talk about hair, what we're saying is actually maybe there's complications. Every theoretical physicist knows having hair is a real nuisance. It's difficult to make it look any good. And so when we say a black hole has hair, we just mean it has sort of extra things that you need to worry about, as well as just those three numbers.
Okay, so they're not actually like a hairy hole at the middle of the universe.
No, sadly not. Sorry.
Okay, but that's shot down my ideas anyway. So how does Stephen Hawking come into this?
The whole question was originally posed by Stephen Hawking in a way, because he was, I think earlier on, Matt Middleton was mentioning Hawking radiation. That's the one mechanism we know of by which you can get rid of a black hole, that very slowly a black hole will throw off bits and pieces, and then eventually it loses all its mass and it actually disappears if you wait a very, very, very long time. And that was really one of Stephen Hawking's great discoveries in theoretical physics. But he immediately realized that it poses a kind of strange question, which is that in physics, we normally think that information can't be lost. So say I chuck something into my black hole. So, I think earlier on Georgia was threatening to throw herself into a black hole. So let's suppose she does that, and let's suppose she weighs, 60 kilograms or something like that. Then the black hole has grown by 60 kilograms. Now, equally well, we could get it to do that by throwing in a sack of potatoes that weighed 60 kilograms. And really, the black hole wouldn't then know any different because, as I was saying earlier on, it's just got these three numbers. So all that's happened is its mass has gone up a bit. Then, according to Stephen Hawking's Hawking radiation idea, later on, the black hole disappears. And somehow, all the complexity about Georgia that makes her different from a sack of potatoes has been completely lost. And that sits very uncomfortably with our normal ideas in physics that actually you can't lose information. If you have a complicated thing sitting there, you can't just get rid of all of that complexity. So this poses the question, how can it be that you lose information?
Sort of what things were, what things were like.
Exactly. Yeah. Where's it gone? And so for a long time, Stephen Hawking said, well, tough, deal with it. The information's lost. It's a new law of physics. But
I love physicists.
Theoretical physicists.
Yeah. We'll just make up another equation just to explain it.
Well, when you're stuck, you sort of have to. But he changed his mind. He said, well, maybe looking at the way things are going, looking at new ideas people have about how black holes really work, maybe somehow or other that information isn't completely lost. And now what he's saying is the information is somehow stored. And it's stored in a very subtle way so that you couldn't really look at a black hole and tell that Georgia had fallen into it. But in a very, very subtle way, on the event horizon itself is stored a very faint imprint of the fact that it was Georgia and not a sack of potatoes that fell into that black hole.
And so presumably this is the metaphorical hair, the sort of the fringe round the edge that has all this information in it.
Exactly. You've turned Georgia into hair.
But if black holes do actually record this, I mean, what does this mean for our understanding of black holes, of the universe, of the theories of physics that we have?
If you can make sense of the way that a black hole behaves without losing information, then it really points us towards the next level of understanding of black holes. And in particular, what we really want to bring in is what we call a quantum theory of gravity, combining Einstein's ideas about warping space and time with the other great development in the 20th century, which was this idea of quantum mechanics. Historically, it's been very hard to fit those things together. And perhaps as we begin to understand these very extreme objects, we'll slowly begin to understand actually how should these things fit together and what does a better theory of physics actually look like.
And sort of very briefly, obviously the theoreticians come up with all their theories and all of that kind of stuff, but to find out if that is how the universe is working, you need to test it. Can you explain how could we actually test whether this information is stored?
Oh dear, yeah, that's pretty hard. There's a reason why theoretical physicists are called theoretical physicists. You know, they really try and push the boundaries of theory forward, but don't necessarily come up with the tests. So typically the tests are a long way behind. But I mean, if you look at what's happened with black holes, it was thought that the whole idea of black holes was untestable. But now we're thinking things like the Event Horizon Telescope. So maybe one day.
Maybe one day. Thank you very much, Andrew Ponson, and thank you also to Manda Banerjee, Shep Dolman and Matt Middleton.
You're listening to The Naked Scientists with me, Chris Smith, and with Kat Arney.
Now, it's time to wrap up the show with our question of the week. Felicity Bedford has been looking into this question from Gaiath.
The Naked Scientists Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from alpha to omega.
Why do humans have such a variety of appearances?
I spoke to population geneticist Sir Walter Bodmer from Oxford University, who is characterising thousands of faces as part of the People of the British Isles project.
You've hardly ever, I imagine, unless you're a member of a pair of identical twins, seen anyone who just looks like you do. So we are enormously variable in facial features. And we don't definitely know why that is, but it obviously has a strong evolutionary basis. There must be something that's selected for that. I think it's part of the way that humans have evolved socially, that it's been very important to be able to recognize people who are part of your own group, even your own family. There are very special regions of the brain for identifying faces, and there are complex processes by which we actually analyze and discern what it is in a face that we recognize.
How much of that variability is down to genetics?
Well, nearly all of it. If you've ever seen identical twins, they've got exactly the same genetic makeup. And when you see them the first time, if you're not their parents or anything, they're almost impossible to distinguish from each other. And that tells us that the face is very largely genetically determined. Obviously, you can vary it. You can have blue hair if you want. You can do things to your face if you go to the right sort of surgeon. But by and large, most of the features that we recognize in a face are very much genetically determined.
When we look at other animals, we don't pick up on as much variability perhaps in their facial features. Is this something which is unique to humans?
No, I don't think it is. But remember, if you go to another country, if you go to Africa or you go to China, you probably don't find it as easy to recognize the facial differences there as you do in your own group. So that's one thing. We don't necessarily know how to recognize that chimps may look very different to each other. So there's undoubtedly a lot of variation there. Of course, if you take domesticated animals like dogs, a lot of the variation has been selected for. So I think there is quite a lot of variation out there. Most of it we don't quite know how to recognize.
Life would certainly be more challenging if we couldn't recognise each other. Our next question is from Che Gianni, who got in touch via Twitter.
Why is it that our voices sound so different to how we think we sound?
Something everyone who works in radio would love to know. If you have ideas, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join the debate on the forum, nakedscientist.com/forum.
That's it for this week. Thank you very much to Georgia Mills for production. Do join us next time when we'll be finding out whether we really can feed, in 2050, up to 12 billion people, which is the predicted world population. The Naked Scientist comes to you from Cambridge University, where it's supported by the EPSRC, the STFC and Rolls-Royce. I'm Chris Smith. And until next time, goodbye.